So, in this lecture we shall be talking about some of the algorithms for floor planning. Okay. So, floor planning algorithms. We shall be briefly looking at several broad classes of algorithms, like you will see that some of them are integer linear programming based, some of them are based on some particular data structures like rectangular, dual graph, then hierarchical tree. Simulated annealing is a very, you can say, common method which gives very good results, and there are some other variations. So, integer linear programming we shall not go into much detail. The basic idea is that we model the problem as a set of linear equations. Not only that, we also specify some cost function, some objective function that is to be optimized, and we give it to an ILP solver. The ILP solver will provide us with the optimum solution, because ILP solver, whatever solution it gives, it is the best possible or the optimum solution. So, the optimality of the solution is guaranteed, but however, the computational complexity is very high, and therefore, it can be used only for very small problem instances. So, for practical problems you cannot really use this. Okay. Rectangular dual graph approach, this is a very interesting approach. You can see here we utilize the linkage of floor planning with partitioning. Typically, when partitioning is carried out, the output of the partitioning process is represented by a graph. Floor plan is obtained by converting the graph into its rectangular dual. Now, let us first very quickly see what this rectangular dual means. Okay. Let us take an example. Let us start from the other way around. Let us start with a floor plan. Suppose I have a floor plan like this, and these are the different blocks A, B, C, D and E. So, when we talk about rectangular duality, the idea is that every rectangular region in this diagram or in this figure will correspond to a vertex. So, which I am shown like this, there will be 5 vertices, and every pair of blocks which have a common boundary, like you see A and B is having a common boundary. So, there will be an edge connecting these two vertices. A and C is having a common boundary. So, there will be an edge connecting this. B and D is sharing a common boundary. D and C is sharing a boundary. D and E is also sharing, and C and E is also sharing. Okay. Not only that, B and C is also sharing. But here, so we have drawn this graph from the floor plan, but actually what is done is the other way around. You will be given this graph, which will be the output of the partitioning problem, that is what we just now said. So, the graph will be like this. Then from this graph you will have to translate it into a floor plan. Now, it is not difficult to do it. Given a planar graph like this, you can convert it with a rectangular dual, replacing every vertex by a rectangular region, and you will be getting the floor plan like this. Now, this is the output of the partitioning problem, where each vertex will indicate the blocks and the edges will indicate the number of connections between them, the weights of the edges, that how strong they are connected. Okay. This is the idea behind rectangular duality. So, just as we have seen, the rectangular dual of the graph satisfies the properties. Each vertex in the graph will correspond to a distinct rectangle in the floor plan, and for every edge the corresponding rectangles, they are adjacent, they will be sharing some horizontal or vertical segment. Now, this is another example we have shown. This is a floor plan and this is the rectangular dual graph. Now, one property you can see, this you can work out with other examples by hand yourself also, that you take any such planar floor plan, rectangular floor plan, you convert it into the dual graph, you will see that the dual graph will consist of a set of triangular regions. This is called a planar triangular graph. Planar means it can be laid out on a plane without the edges crossing each other. Okay? So, planar means you can lay out the graph on a plane surface, the edges will not be crossing each other. Because the floor plan was planar, the graph you are embedding on it, it will also be a planar graph. Okay? So, it is automatic and all the faces will be triangular in nature. This is the property. So, this graph will essentially be a planar triangular graph which you have to translate into a floor plan. Now, there are a few things. Now, if you have a floor plan with a cross junction, see, this will not correspond to a planar triangular graph, because 1 and 2 are adjacent, 1 and 4 are adjacent, 2 3 and 3 4. So, it will look like this, but 1 3 and 2 4 they do not share any horizontal and vertical line. So, if we have a situation like this, you do not get a PTG, but if you have a situation like this, so what you can do, if you slightly shift this edge 3 4, if you shift it slightly like this, then there will be a sharing between 2 and 4, there will be edge between 2 and 4 coming in, right. So, PTG is a property which you must have, and from PTG you can translate it into this graph. Okay. Now, there is one problem though, that every planar triangular graph cannot be translated into a floor plan. This is the one and only one problem case. This is called a complex triangle. This actually indicates a complete graph of 4 vertices drawn like this. There are 3 triangular faces. Now, you can try it out in any way, you will see that you cannot draw a floor plan for which the corresponding dual graph will be this. So, this complex triangle is one difficult problem in this particular approach whenever you encounter it in a graph. So, let me just tell you first. So, here what we are saying is that we start with that graph which our partitioning algorithm is giving us, some blocks and their interconnections indicating their strength of connections. Now, if we have the planar triangulations in that graph, you can map it to a layout or a floor plan. So, this you will always be having, but if you have a complex triangle there, you cannot map that subgraph into a rectangular dual into a floor plan. So, this is one of the drawback. This is an interesting approach to floor planning, where we start with a graph representing a partition and from there we translate it into a floor plan, but the main issue is the issue of complex triangle. So, what we do, one possible heuristic that has been proposed is something like this. You consider the complete partitioning graph, you identify all complex triangles that exist there, you select one edge from each of those complex triangles, and in each of the edges you add one edge, which means it is something like this. Like say your complex triangle looks like this. So, what we are saying is that in any one of the edges you add a vertex and you add a dummy edge here. So, this is no longer a complex triangle. Okay. So, your that complex triangle problem is solved if you add dummy vertices like this. So, the problem solution suggests this, you add such dummy vertices, but again determining the minimum set of weight this kind of edges that can eliminate all complex triangles is also proved to be a difficult problem, but however some heuristics are available and some tools have actually used this kind of a heuristic to create a floor plan, right. Okay. This hierarchical approach is an interesting approach which also is quite commonly used. So, here what we say is that we use some kind of a divide and conquer approach. That means, we divide the problem into smaller sub problems which are easily manageable. Like we consider a small graph with 3 vertices, that means 3 blocks. So, these 3 blocks can be placed in 3 possible ways. Okay. So, what we are saying is that if we have a small set of blocks, we have a graph like this, we have the properties of A, B and C, what are their areas and their properties, how they are connected. So, you can explore the alternate floor plans and find out which one of these 3 is the best. Suppose you find that the last one is the best. So, you freeze on this and you merge this ABC into a single macro node, which means you have already solved this sub problem. ABC can be best laid out in this fashion, right. The other 2 you ignore. This is the basic idea. So, after the optimal configuration for the 3 modules are determined, as I said, you merge them into a single module. So, in the next higher level, that single so called super vertex will be there and you go on repeating this. But the problem here is that, as I said, you are considering small number of vertices at each step, but how small? 3, 4, 5, 6? Well, it is seen that the number of such possibilities, they increase very rapidly with the number of vertices. So, typically we limit the number of nodes to 5, not more than that. The number of possible floor plans increases exponentially with d. D is the number of vertices in the graph. So, just an example, for d equal to 2, these are the 2 possibilities. For d equal to 3, you can have 6 possibilities. In this way, it goes very rapidly as you move to d 4 or 5. Okay. So, the idea is that if you have a graph of that size, you try to find out, explore all possibilities and find out the optimum configuration of the floor plan. Take it, freeze it and merge all the vertices into a single super vertex for the next level, right. So, bottom up is the natural approach in this hierarchical method. So, modules we represent as vertices in the graph, while the edges will indicate connectivity, the edge weights. So, the modules which have higher weights, the pairs of modules, they will be clustered together with the restriction that number of modules in each cluster will be limited to d. This d is our limit. Like the idea is this, we have a graph, each vertex indicates our blocks, the edges, the weight of the edges indicates how many connections are there between the blocks. Suppose I select a set of d such nodes which are strongly connected. You take that set of d nodes, place them optimally, because you know all possibilities, explore all the possibilities, find out which floor plan configuration gives you the minimum cost. Take that and replace those 5 nodes by a single macro node, but limit that number to d equal to 5. Okay. So, the exhaustive enumeration is done at every step. This cluster is merged into a larger module for higher level processing. Repeat this process. Now, this is of course a greedy procedure where you sort the edges and decreasing weights typically. The heaviest weight indicating the strongest connectivity will typically be chosen first, and the modules are clustered in a greedy fashion, and this is repeated. I shall be showing this with an example, that how this is done. Okay. So, let us take an example. Okay, I will just come back to this. Let us take this example first. This is a graph with 5 vertices. The weights of the edges are shown. So, you can see that in a greedy clustering approach, the vertices which are most strongly connected, like A and B, C and D, you merge them together. You put A and B together, you put C and D together. So, once you do it, you only are left with E, so which is relatively weakly connected 2 and 1, okay, with these clusters. Now, what happens is that this AB gets connected together, CD gets connected together, but you do not have anywhere to place E. So, in this greedy clustering, possibly E will be placed on the right. So, you will be getting a lot of empty spaces on top and bottom. Okay. So, one heuristic that has been suggested is that this is a problem. Some lightweight edges may be chosen at higher levels in the hierarchy, resulting in adjacency of 2 clusters of incompatible areas that may lead to an increase in the layout area. Like you see here, this E, this AB and CD are nicely compatible in terms of the height. So, E you cannot place anywhere down. So, you have to place it on the right. Okay. So, this happens. Now, this heuristic says, so if you see that a cluster is connected to a neighboring cluster with a very small weight, you club them together initially. This is just a heuristic. Okay. The idea is that you see D and E are very weakly connected with a weight of 1. You club D and E together at the beginning itself. So, D and E will be side by side. Okay. Now, you use the rest, A and B together, C and D together. So, here you will see that the solution we get will be more compact, because D and E, because they are together, you can place it just below C, but here because C and D are merging, D will be placed just to the center of C below it. So, you do not have enough space to keep E either to the right or left, okay. But here it happens. So, this is just a heuristic which gives reasonably good solution. Now, top down is the other alternative. So, here you start from the partitioning process. So, you start from the whole netlist. So, the idea is this. So, you have the entire netlist that corresponds to your complete floor plan. You partition this netlist into 2 parts. In the floor plan, this corresponds to 2 parts. You partition this into 3 parts, let us say. Here itself you partition the floor plan into 3 parts. Here you partition it into 2 parts. Here you partition in 2 parts. So, there is a one-to-one correspondence. Top down you are partitioning the netlist, and at the same time in a corresponding fashion you are also partitioning the floor plan. So, you will be getting, let us say these are A, B, C, D and E. So, you will be getting exactly where in the floor plan you will be placing them, right. So, this is the top down approach. But the major issue is that we have seen the Karnighan-Lin partitioning algorithm, which divides a graph into 2 parts. But here in general we need a method which can partition a graph into more than 2 parts, but such good algorithms are not very commonly available. We have to use heuristics and approximation methods. So, KOA partitioning it is called. So, there are algorithms for KOA partitioning which can be used here, which divides a netlist into k different parts, but again the computational complexity to obtain good solutions there is quite high. that is one problem. Because of that, this is not very widely used. Balanced partitions is difficult to obtain. Balanced means the partitions of equal sizes, so it is difficult to get, right. Okay. Simulated annealing is an interesting method. So, simulated annealing is a very commonly used method which is used in VLSI CAD in other applications also. This models the annealing process of metals. So, this is basically an optimization problem, a solution to an optimization problem, where you have a solution. We start with a solution, we have a set of moves that can take us from one solution to the other, and we have a cost function in which you can evaluate. This means for a given problem I have my solution, that is means that we have a solution representation. It is an iterative process. At every step we make some small changes in the solution, these are called moves. After making the change, we check whether we are getting a better solution or not. If we get a better solution, there is a cost function, we can check using that. If we get a better solution, we always accept it. But if we get a worse solution, then also we may accept it, but that probability will decrease with time. This is called the annealing process or the cooling process in metals, whatever it is called. So, this is the basic idea behind the simulated annealing algorithm. Okay. So, in this method for floor planning, the floor plan is represented by a tree, and the polish notation that I talked about earlier, that postfix notation, that same kind of postfix notation is used for representation and also for manipulation of the moves. So, let us see how. So, this notation I am just repeating for a convenience. This I and j indicate two blocks. I, j, h means something like this. This I and j are connected by a horizontal line, I and j. This will denote by I, j, h. Similarly, I, j, v, this means rectangle j is on the left of rectangle I. If I write I, j, v, this will correspond to j is on the left of I, separated by a vertical line. So, every such slice is represented in the polish or the postfix notation like this. Now, we define a normalized polish expression, which says that a polish expression is called normalized if it does not contain consecutive h or v symbols. This is used just for reducing some amount of redundancy, because as we have seen earlier, the same floor plan can have multiple slicing trees or they can have multiple polish notations. So, this is one way to normalize it. Okay. Fine. Let us take an example. This is a floor plan. There are two alternate slicing trees, you can see. You can either merge 1 and 2 first, 3 and 4 first, and then combine them, or you can merge 1 and 2 first, you combine 3 with it, then combine 4 with it. So, the corresponding polish notations will look like this: 1, 2, h, that means dash, 3, 4, v, that means bar, this bar, this bar, this, and similarly for this 1, 2, dash, 3 bar, 4 bar. You can see here there are two vertical notations consecutive, but here there is no such. This one will be considered to be normalized. So, for representation we will be using only normalized expression. Okay. This is what we do. Then some of the parameters like the moves I talked about. So, 3 moves are defined here. The first move says you swap 2 adjacent operands move 2 says you complement a series of operators between 2 operands. This is called a chain. Complement means if it is a V, you make it H, if it is H, you make it V. See, complement a series of operators between 2 operand means, suppose I have something like this, I have a block A, I have a block B, between that say I have dash, bar, dash, let us say. So, what it says, these you replace by bar, dash, bar, complement each of them. Okay. This is called a chain. And the third move says swap 2 adjacent operators and operands. So, if you have A dash, you replace it by dash A, something like this, swap them. And the first one is of course swap 2 adjacent operand, that means if it is A B, make it B A. And the point to note is that after making a move, we will consider it only if it results in a normalized expression, because you can check moves A and B will leave a normalized expression to a normalized one only. Only move C can result in a case where a normalized expression can become unnormalized, like you might be having a situation where it was A dash, let us say dash. So, if you swap these two, it may become dash dash A. So, you may get 2 consecutive dashes, it may become unnormalized. Okay. Fine. So, the cost function again will be very similar. You have area, you have the wire length, then some weighted function. This I have already discussed earlier, same kind of cost function you can use. And this is just an example. Let us say this was an initial solution from where you are starting, this is the corresponding Polish notation. So, I am just illustrating one possible sequence of moves. You make move A, which means you are swapping 2 operands, this 4 and 3, you make it 3 and 4. So, what will happen? 3 will come here, 4 will come there. So, you get a solution like this. Move B. So, between let us say 2 and 3, you complement everything, there is only one, you complement it to dash. So, new layout looks like this. Move C, what I do? This 4 and this dash, you swap them, this becomes this. See, this example I have manufactured deliberately just to show you that some sequence of move can result in a very nice final solution, but in the practical simulated annealing case, you will have to do a lot of such iterations, lot of trial and errors, and you will possibly arrive at a good solution at the end. But this example actually shows you that it is possible to find a sequence of moves through which from a bad solution you can go to a good solution. And lastly, let us just talk about rectangular and L-shaped blocks. You see, the block shapes can be anything, not only rectangle, they can be L-shaped like this. But even if you restrict yourself only to rectangular blocks, whenever you put blocks side by side, it can take the shape of a L like this. And also, whenever you put the blocks in sequence one after the other, you can lead up to a situation as it is shown here, where you get a wheel kind of a structure, non-sliceable. So, although each blocks were rectangle, as we move one after the other you go on connecting, at the end you might get a wheel kind of a structure. Okay. So, these are some complexities you need to consider while generating constructive rectangular floor plans. So, means I have just tried to give you an overview regarding the possible floor planning algorithms without trying to go into the very details of them. So, I think you will have a fair idea regarding the approaches that are followed. Thank you.